2.7 in the book is about implicit differentiation, which is a method for taking the derivative of anything that is not written in explicit form. Okay, and so what I mean by explicit and implicit is if a function is written as y equals and then everything on the right side is in terms of x, that is an explicitly defined function of x. Okay, if y is not isolated, okay, so for example, 3x minus 4y equals 7. We know that's a line, but this is implicitly defined right now because it is not written as y equals and then everything in terms of x on the right side of the equation, okay? So if a function does not have y equals by itself with no other y's on the other side and everything in terms of x on the other side or constant, then it is an implicitly defined function. Okay, so what we're going to do is look at how we can take the derivative without solving for y, because there are some equations, maybe they're functions and pass the vertical line test, maybe not, but we still need to be able to take the derivative. Okay, so think about a curve like a hyperbola. Okay, so let's say we have something like this. All right, well, this is not a function because it fails the vertical line test, but that doesn't mean we shouldn't be able to figure out how to write the slope of the tangent line at a particular point. So we still need to be able to find the derivative. Okay, so we've mentioned Leibniz notation a couple of times, and we've talked about how this is the same thing as writing the derivative with respect to x of y. Okay, so if y prime is the derivative with respect to x of y, then using that same notation, x prime should be the derivative with respect to x of x, or in other words, dx over dx. Okay, now when you look at this, you should be seeing, hey, this is the same thing on the top and bottom. And again, d and x do not represent variables. Like we don't have the variable d times the variable x. This dx by itself means the differential of x, but still you can see that we have the same thing on the top and bottom, and something divided by itself is equal to 1. Okay, so x prime, the derivative with respect to x of x, is equal to 1, which, if you think back to 2.3 in the book where we talked about the derivative of the constant, the derivative of the identity function, which is y equals x, and the derivative is always 1, and then we did the product and sum rules and all those, we know that the derivative of x is 1. If we think about it visually, a line that is y equals 1x has a slope of 1. So the derivative of x, again, is 1. Okay? But the reason I'm pointing this out, which just seems pretty obvious, is because our process for differentiating implicitly is going to be to go through the equation, take the derivative of every term using the variable that is present where it is. Okay, but then we may need to use the chain rule if our variable is not an x. All right, so what I mean by that is, let's look at this first example to make it a little bit easier. Okay, so what I mean by that is, when I take the derivative of this, because this is a y and not an x, I'm going to have to attach the derivative of y to that. And I'm going to use two different notations to write this. The first one is going to be very similar to how we wrote our composition of functions with the chain rule, where if a function is written as f of u, where u is the function on the inside, then when we take the derivative, we have f prime of u times u prime. So I'll use that u prime notation. It just won't be the letter u. All right. And then the second way is going to use the Leibniz notation. Okay. Before we do that, though, just to simplify this equation a little bit, let's get rid of this square. We can take the derivative of cosecant squared, but just to simplify things, let's just call that cosecant y for now. All right, so that has nothing to do with taking the derivative. That's just me changing the original problem. All right, so taking the derivative of everything in this equation exactly where it is. I'm starting here. The derivative of y cubed, using the power rule, is going to be 3y squared. Now, if this is, let's say the outer function is going to be, so we'll say f of u is equal to u cubed, and then the inner function u is just y, okay? Then taking the derivative, I get 3u squared, so in this case 3y squared, but then I would have to multiply by the derivative of what's on the inside, which in this case would just be y, so I'm going to write that as y prime. Okay, so I used the power rule here, but then I had to multiply by y prime because of the chain rule. which tells me to take the derivative of the inside and multiply it. All right. Hopefully this will be more clear as we do more. For x to the fifth, the derivative there is going to be 5x to the fourth with the power rule, and then I'll multiply by, think of it as the function on the inside being x prime. Well, the derivative of x prime is just 1, so I would write times 1. Okay, now you don't really need to write times 1, but you could even put x prime if you want, but x prime is 1. Okay, for this side, 10 is a coefficient, and then the derivative of cosecant y is negative, with 10 is a coefficient, but I'm putting the negative in front. Cosecant y times cotangent y, but then again, using the chain rule, since our inside function is y, we need to multiply by the derivative of that, which is y prime. All right, and then at this point, my goal is to find y prime. So I'm not done, even though I've taken the derivative. I need to do some algebra to get y prime by itself. Okay, so to do that, I'm going to move everything with y prime to one side and anything that doesn't have y prime to the other side. In this case, the 5x to the fourth does not have a y prime, and the 3y squared and the negative 10 cosecant times cotangent does. So I'm going to move this to, actually, to make things positive, I'll move this, everything here to the left and this to the right, and then I'm going to factor y prime out. So I have y prime times 3y squared, and then plus this 10 cosecant y times cotangent y. Okay, and I've got the y prime factor to the front, and then over here equals 5x to the fourth. Last step, because I'm solving for y prime, is I need to divide the entire equation by everything inside the parentheses, and I get y prime equals 5x to the fourth all over 3y squared plus 10, cosecant y times cotangent y. And that is my derivative. Now, I did say I was going to write this two different ways, so let me move these down a little bit. Okay, the other way is using the Leibniz notation. For that, think of this as taking the derivative with respect to x of this entire equation. Okay, so starting with the first term, the derivative of y cubed with respect to x is 3y squared times, and then derivative of the inside is dy over dx. Okay, minus, and then for the derivative of x to the fifth, I have 5x to the fourth times the derivative of x with respect to x. I'm using the chain rule with each piece. And then equals negative 10 cosecant y times cotangent y times derivative of the inside dy over dx. So with every term, whatever variable that was there, I multiplied by the derivative of that with respect to x at the end of each. Okay, now dx over dx is 1, so I didn't really have to write that, but I did for this first one. Okay, and then I still need to solve for dy over dx, so I'm going to do algebra the same way I did before. So 5x to the fourth moves to the right, this whole expression moves to the left. I factor the dy over dx to the front and get 3y squared plus 10 cosecant y times cotangent y equals 5x to the fourth, and then for my last step, I divide the entire equation by everything over here, and I have dy over dx equals, running out of room here, but it equals exactly what I had up there. Okay, now I don't care which notation you use, but what you need to keep in mind is whenever there is a term that is not the variable with which you are taking the derivative with respect to. That was a weird way to say those prepositional phrases there, but if it's the derivative with respect to x and your variable is not x, or if we were taking the derivative with respect to t and your variable was not t, you need to attach the derivative of the given variable with respect to the desired variable to every term that has that. Okay, so for part B, okay, I'm going to use the first notation that I did here. For part B, I'm taking the derivative with respect to x, okay, but I'm going to have to multiply anything that involves the y's by y prime. If I take a derivative of something that has a y, I need to attach a y prime. Okay, so derivative of y cubed is 3y squared times y prime, minus the derivative of 6x squared is 12x. I do not need to write times x prime. If I did, it would just be 1 in the next step anyway, okay? Plus, now for x times y, those are both variables, I need to use the product rule. So it's going to be x times the derivative of y, which is 1 y prime plus y times the derivative of x, which is just 1, or again, you could write x prime if you want, okay, and then equals, over here, I can do this one of two ways. For simplicity, I'm going to go ahead and move the 10 down, so then I just have 10 times the natural log of y, so I get 10 times 1 over y, which is 10 over y, but then I multiply by y prime. Okay, so then moving some things around, anything that has a y prime, I'm going to move to the left. Anything that doesn't, which is this and this, is moving to the right. So then over here on the left, I have y prime equals 3y squared. That's moved over, plus x, and then minus 10 over y. And then on the other side, I've got a positive 12x minus 1y. Okay, now if we were doing this with the dy over dx notation, okay, it would be the same thing. We would just be factoring the dy over dx over to this side. Lastly, y prime is equal to, and I need to take this, divide by all of that. So we have 12x minus y over 3y squared plus x minus 10 over y. This is kind of gross. I don't want a fraction inside a fraction, so to clean that up, I'm going to multiply by y on the top and bottom because that's the least common denominator, and I'll get 12xy minus y squared all over 3y cubed plus xy minus 10, and that is my derivative. Okay, now there's a handful of things that implicit differentiation is good for. We're going to use it in some upcoming sections to derive formulas that are going to make a lot of other functions easy to differentiate, like transcendental functions. Okay, but another thing that it is good for is it can simplify our process for taking the derivative even if a function is explicitly defined. So what I mean by that is, let's look at this next one. This is explicitly defined because it's y equals, and then this is f of x, a function of x. Everything on the right side is an x. If I want to take the derivative using my known rules, however, I'm going to have to use the quotient rule. Within the quotient rule, I have a chain rule here and here, and then I also have a product rule up here. So I'm going to have the denominator times, and then when I do the derivative of the numerator, I'll have the product rule and then the chain rule within the product rule, and then minus this whole thing times the derivative of the denominator, which means chain rule again, all over this whole thing squared. That sounds very gross and tedious. So to avoid that, I want to rewrite my equation in such a way that it is algebraically equivalent, but I can break all these things apart. And our option for that is using log properties. Okay, so I can take the natural log of both sides of this equation and write it as natural log of y equals the natural log of this whole thing, but log properties tell me that if I have a natural log of and then a product or a quotient inside the log, I can split that with addition or subtraction into separate logs. So I'm going to have the natural log of x cubed plus the natural log of x squared plus 1 to the fourth minus the natural log of x cubed minus, square root of x cubed minus 1. Okay, so already this is looking better because now, even though I have more terms, I'm not going to have to use the product and quotient rule. Okay, now there's one more thing that log properties can help us do, and it's totally fine to do this in one step instead of two. I just wanted to do a little bit at a time here. Okay, is we can use the power rule or the power property for logs and take these exponents and move them down to the front. So we can actually write it as 3 times the natural log of x plus 4 times the natural log of x squared plus 1 minus 1/2, because that's a square root, times the natural log of x cubed minus 1. Okay, now we can take the derivative with respect to x of this whole equation, and the derivative on the right side is going to be a lot easier to do. Okay, now derivative on the left side, I have 1 over y times y prime, or again, you can write dy over dx, equals, and now I'm looking over here, okay? The derivative of 3 times natural log x is 3 times 1 over x, which is 3 over x, okay? The derivative of 4 times natural log of x squared plus 1 is 4, I forgot my plus sign, plus 4 over x squared plus 1. Now I do need to use the chain rule because there's a composition in here. So this is like my u, meaning I need to multiply by u prime, which is 2x. Okay, I can combine those and make it an 8x now, or I can do it later. All right, minus 1/2 times 1 over x cubed minus 1. And again, I've got a chain rule, so I need to multiply by the derivative of this, which is 3x squared. Okay, so I can move that over and I can distribute this too if I want. But as far as solving for y prime goes, the only thing I need to do is get rid of the y. Okay, so I'm going to multiply both sides of the equation by y and write this as y prime equals, and I'm not going to distribute because that would be messy, so I'm going to write this as 3 over x plus, multiplying those, 8x over x squared plus 1 minus 3x squared over 2x cubed minus 2, distributing down there. And then that whole thing is times y. Now, this is the important part. If a function is explicitly defined to begin, I cannot leave y in my final answer. If it is explicitly defined, then y prime also needs to be explicitly defined because it is a function. And so I need to write my answer as a function f prime of x, not f prime of x and y. Okay, now we can do this pretty easily, just takes a little more writing. We need to replace this with f of x. Okay, so, and again, not distributing because that's messy. 3 over x plus 8x over x squared plus 1 minus 3x squared over 2x cubed minus 2. All of that times the original f of x, which is x cubed times x squared plus 1 to the 4th over root x cubed minus 1. And then this is y prime, the derivative. Okay. All right, one more example here. I want to look at a higher order derivative. We have x squared plus y squared equals 25. We know that that's a circle centered at the origin, radius of 5. To find the second derivative, we need to take the first derivative, solve for dy over dx, and then take the second derivative. So I'm going to do this implicitly. My derivative here is going to be 2x, okay, and you don't need to write times 1 or times x prime or times dx over dx, plus derivative here would be 2y times y prime, or again, dy over dx, equals derivative of 25 is 0. Okay, so to solve for y prime, I'm going to subtract 2x from both sides. Okay, and I'll have, 2y times y prime equals negative 2x. So dividing both sides by 2y, I get y prime is equal to negative x over y. So this is my first derivative. And then to take the second derivative, I need to take the derivative of that expression, or both sides of that equation, okay? So I'm taking the derivative with respect to x of this whole thing. All right, so that's going to give me the second derivative, which we can write as y double prime, or you can write it as d squared y over dx squared. I'll use that notation since that's what's in the problem. D squared y over dx squared, okay, equals, and now the derivative of this side, I need to use the quotient rule for, okay? So it's going to be y times the derivative of negative x, which is negative 1, minus negative x, I'll go ahead and make that plus x, times the derivative of y, which is y prime, or dy over dx, all over the denominator squared, okay? Now here's the thing. Your second derivative cannot have a notation for the first derivative in it, so we need to get rid of this. Now we can't just delete it or ignore it, but what we can do is we can replace it with what we know dy over dx to be. Okay, so replace with dy over dx, which is negative x over y. Okay, so we get y times negative 1 plus x times negative x over y, we'll clean that up in a second, all over y squared. All right, and to simplify this, again, I'm going to multiply top and bottom by the least common denominator, which is y. So I get negative y squared minus x squared, okay, because that y cancels, all over y cubed. And this is my second derivative.